In this video, I want to tell you about a couple special matrix operations called the matrix inverse and the matrix transpose operation. Let's start by talking about matrix inverse. And as usual, we'll start by thinking about how it relates to real numbers. In the last video, I said that the number 1 plays the role of sort of the identity, right, in the space of real numbers because 1 times anything is equal to itself. It turns out that real numbers have this property that every number that each number has an inverse. For example, given the number 3, there exists some number, which happens to be 3 inverse, so that that number times 3 gives you back the identity element 1. Right? And so, 3 inverse, of course, this is just 1/3, right? And given some other number, maybe 12, there's some number which is the inverse of 12, written as 12 to the minus 1, or really this is just 1/12. So that when you multiply these two things together, right, the product is equal to the identity element 1 again. Now, it turns out that in the space of real numbers, not everything has an inverse. For example, the number 0 does not have an inverse, right? Because sort of 0 inverse, so 1 over 0, that's undefined, right? Because 1 over 0 is not well defined. And what we want to do in the rest of the slide is figure out what does it mean to compute the inverse of a matrix. Here's the idea. If A is an m by m matrix, and if it has an inverse, I'll say a little bit more about that later, then the inverse is going to be written a to the minus 1, and a times its inverse, a to the minus 1, is going to equal to a inverse times a, is going to give us back the identity matrix. Okay? Only matrices that are m by m for some value of m have an inverse. So a matrix that is m by m, this is also called a square matrix. And it's called square because the number of rows is equal to the number of columns. Right? And it turns out only square matrices have inverses. So if A is a square matrix, so it's m by m, and if it is inverse, then it satisfies this equation over here. Let's look at a concrete example. So let's say I have a matrix 3, 4, 2, 16. So this is a 2 by 2 matrix. So it's a square matrix, and so this matrix could have an inverse. And it turns out that I happen to know the inverse of this matrix is 0.4 minus 0.1 minus 0.05, 0.075. And if I take this matrix and multiply these together, it turns out what I get is the 2 by 2 identity matrix, I. I can write this as I 2 by 2. Okay? And so on this slide, this matrix is the matrix A, and this matrix is the matrix A inverse. And it turns out that here I've computed A times A inverse. It turns out if you compute A inverse times A, you also get back the identity matrix. So how did I find this inverse? How did I come up with this inverse over here? It turns out that sometimes you can compute inverses by hand, but almost no one does that these days. And it turns out there's very good numerical software for taking a matrix and computing its inverse. So again, this is one of those things where there are lots of open source libraries that you can link to from any of the popular programming languages to compute inverses of matrices. Let me show you a quick example how I actually computed this inverse. And what I did was I used software called Octave. So let me bring that up. We'll see a lot more about Octave later. But let me just quickly show you an example. I'm going to set my matrix A to be equal to that matrix on the left. So I'm going to type 3, 4, 2, 16. So that's my matrix A, right? It's this matrix 3, 4, 2, 16 that I have down here on the left. And the software lets me compute the inverse of A very easily. I'm going to type P inv of A equals this. And so this is, right, this matrix here, 0.4 minus 0.1, and so on. This is giving me a numerical solution to what is the inverse of A. So actually, let me just write inverse of A equals P inv of A. So I've set inverse of A over that. I can now just verify that A times A inverse the identities. And type A times inverse of A, and the result of that is this matrix. And this is 1, 1 on the diagonal, and essentially what, 10 to the minus 17, 10 to the minus 16. So up to numerical precision, up to a little bit of round-off error that my computer had in multiplying these two matrices. So up to little numerical round-off, these numbers off the diagonals are essentially 0. And so A times the inverse is essentially the identity matrix. And I can also verify inverse of A times A is also equal to the identity with ones of the diagonals and values that are essentially 0 except for a little bit of round-off error on the off diagonals. In my definition of the inverse of a matrix, I had this caveat, right? First, A must always be a square matrix, but I had this caveat of if A has an inverse. Exactly what matrices have an inverse is beyond the scope of this linear algebra review, but one intuition you might take away is that just as the number 0 doesn't have an inverse, it turns out that if A is, say, the matrix of all zeros, then this matrix A also does not have an inverse because there's no matrix, or there's no A inverse matrix, so that this matrix times some other matrix would give you the identity matrix if this is a matrix of all zeros. And there are a few other matrices with properties similar to this that also don't have an inverse. But it turns out that in this review, I don't want to go too deeply into what it means for a matrix to have an inverse, but it turns out that for our machine learning applications, this shouldn't be an issue. Or more precisely, for the learning algorithms where this may be an issue, namely whether or not an inverse appears, I'll tell you when we get to those learning algorithms just what it means for an algorithm to have or not have an inverse and how to fix it in case we end up working with matrices that don't have inverses. But the intuition, if you want, is that you can think of matrices as not having an inverse if it's somehow too close to 0 in some sense. And to give just to wrap up the terminology, matrix that don't have an inverse are sometimes called a singular matrix or degenerate matrix. And so, this matrix over here is an example. The 0, 0, 0 matrix is an example of a matrix that's singular or a matrix that's degenerate. Finally, the last special matrix operation I want to tell you about is the matrix transpose. So suppose I have matrix A. If I compute the transpose of A, that's what I get here on the right. This is A transpose, which is written A superscript T. And the way you compute the transpose of a matrix is as follows. To get a transpose, I'm going to first take the first row of A, 1 to 0. That becomes this first column of the transpose. And then I'm going to take the second row of A, 3, 5, 9, and that becomes the second column of the matrix A transpose. And another way of thinking about how to compute the transpose is as if you're taking this sort of 45-degree, axis and you're mirroring or you're flipping the matrix along that 45-degree axis. Okay? So here's the more formal definition of a matrix transpose. Let's say A is an M by N matrix, and let's let B equal A transpose. So let me say B equals A transpose like so. Then B is going to be an N by M matrix with the dimensions reversed. So here we had a 2 by 3 matrix, and so the transpose becomes a 3 by 2 matrix. And moreover, Bij is equal to Aj. So the Ij element of this matrix B is going to be the Ji element of that earlier matrix A. So for example, B12 is going to be equal to, look in this matrix B, B12 is going to be equal to this element 3, right? First row, second column. And that's equal to this, which is A21, second row, first column, right? And, which is equal to 2. And it's another example, B32, right? That's B32 is this element 9. And that's equal to A23, which is this element up here, 9. And so that wraps up the definition of what it means to take the transpose of a matrix. And in fact, that concludes our linear algebra review. So by now, hopefully you know how to add and subtract matrices as well as multiply them, and you also know how what are the definitions of the inverses and transposes of a matrix. And these are the main operations you need in linear algebra for this course. In case this is the first time you're seeing this material, I know this was a lot of linear algebra material, all presented very quickly, and this is a lot to absorb. But but there's no need to memorize all the definitions we just went through. And if you download a copy of either these slides or of the lecture notes from the website, from the course website, and use either the slides or the lecture notes as a reference, then you can always refer back to the definitions to figure out, what are these multiplication, transpose, and so on definitions. And the lecture notes on the course website also has pointers to additional resources on linear algebra, which you can use to learn more about linear algebra by yourself. And next, with these new tools, we'll be able, in the next few videos, to develop more powerful forms of linear regression that can deal with a lot more data, a lot more features, and a lot more training examples. And later on, after linear regression, we'll actually continue using these linear algebra tools to derive more powerful learning algorithms as well.